Well, Assalamu alaikum. It's my pleasure to be here and presenting a 5 webinar series on my book, which I published together with a distinguished professor from UAC, Tokyo. And so this is the title page of my book, which we are going to discuss in this 5 webinar series. And so I begin with submitting my regards to all my distinguished colleagues, students, participants joining from different OIC countries. It's a great pleasure to welcome you all to this 5-day scholarly webinar series, currently organized by Comstech and Kaidan University. And this series is based on the internationally recognized book authored by me and my colleague, Professor Dr. Shinichi Watanabe from the University of Electrocommunications. So this book is an outcome of 25 years collaboration with the University of Electrocommunications. As a direct product of the work presented in this book, we have brought numerous research areas in Pakistan, which has benefited many generations of students and experts. So this is what we know today all about as quantum technologies in Pakistan, in the world. And we see that in the last 5 years, it has got really good appreciation in the form of more than 6 Nobel Prizes. As a result of this long-standing collaboration with UAC, there is a direct benefit to the students that many generation of students have gone there to UAC and studied at master's and MPhil and PhD levels. And at present, it's interesting to note that at UAC, we have the largest number of Pakistani students in the foreign student community. So it's a good appreciation of our work with this University of Electrocommunication and so on. When we want to divide the book in 5 segments and discuss in the 5 webinars, so I have set a layout that we shall be talking, which we shall be following during these 5 webinar series. So we shall start with basics like understanding the nature of light, and then we shall talk about the atom field interaction, how they really interact, in how many different ways they interact, and what are the basic characteristics we can immediately understand from this interaction. Then we see the application of this in atomic cooling, trapping, interferometry, and many other characteristics. And we come up with, as next chapter, next topic, as the cold atom, ultra-cold atoms interaction with the high-dimensional fields. So this high dimensionality enters when we are coming more and more closer to the real experimental scenarios. So we can't avoid that. And then complex optical systems and the quantum dynamics is a very beautiful, interesting topic, which is basically used in developing various different kind of devices and also various different kind of sensors and even quantum computers today. And then at the end, we shall cover we shall have a summary of present day quantum technologies which we have, including quantum computers coming very fast and almost there. So when we want to talk about the first segment of the 5 webinar series discussion, so the first segment is talking about the quantum nature of light and atom field interaction. And this here we have evolution of the subject as a simple understanding from where we started and what we are knowing about the fields today. And then we talk about the nature of light in the best shape which we understand, how we quantize them, and then what is the outcome of the interaction, how we understand the interaction. So if we go and start the story begins with the basic understanding of human and see how we have the world around us. So at the time of Aristotle, it was an understanding that the radiations are coming from our eyes, and we see. It's a theory of vision, which was named as extromission theory. So this was a very interesting way of thinking, that the radiations are coming from our eyes, and these radiations are coming from our eyes are making us see. This concept stayed with human kind for more than 1,000 years. It's funny. It's interesting because basic experiments could have shown something different. For example, Ibn al-Hashim showed around 1,200 years later, after Aristotle, with his experiments, that actually this is the light which is coming from sun and various different sources and coming to our eyes, and we can see. So it is named as the theory of intromission. And so this was a very interesting extension of the work. So now, exactly after 1,000 years, Richard Feynman extended the statement of Ibn al-Hashim by saying that if you really understand light, you will see that it does not push just your retina, that we can see better, but it pushes the universe. So this is something, this small extension took around 1,000 years to really understand the beauty of light, how and what we can understand. So this extension came with hundreds of year work, which is there in various forms. So in last 1,000 years, Ibn al-Hashim work guided various different people, scientists who are working in optics. So his work was reproduced in various different ways. Many people got advantage, like Newton, Einstein, and so on. And Newton came up with his understanding that these are the particles which makes light. So he came up with the understanding that the light is made up of the particles. But soon after that, there were interference was discovered, and then Maxwell came up with his own Maxwell equations, and he showed that light and electromagnetic fields are basically can be written in the form of waves, which are continuous. So the understanding of Newton was forgotten for some time till we met Planck's work, which is coming later. So in 1901, there were two different experiments. Ernst Nicholas and Gordon Hull and Peter Lebedev independently, they calculated the light pressure which is exerted by light on various different objects. So here radiation pressure was also introduced for the first time, with calculation on which parameters this radiation pressure is based on, and so on. Max Planck came up with an interesting calculation in which he proved that light is made up of particles. Later, Albert Einstein used his work and also associated a momentum concept with the light particles. And in 1926, these light particles were given the name as photons. So basic work of Planck's was very simple. I mean, if we look at the Planck's hypothesis and its work, which was very much a simple extension of previous mathematical work already being done, it was actually replacing integrals by summations. And a very interesting result came up that he was able to see the distribution formula, radiation distribution formula, which was very much supporting the existing experiments. So all previous explanations, which were basically developed on the continuous nature of light, were not working. So he came up with this simple idea that summation can do the same work which is done by the integral in principle. So if we do the same mathematics, so maybe it is simplified, we can get some better results mathematically. And interestingly, these mathematical results were very much satisfying the available experimental results. So from here we got the Planck's distribution, radiation distribution formula, which is known as Planck's law as well. So later discussion proved that this summation is basically is showing the discreteness of light. So this was a very simple transition mathematically, but it was very powerful in developing the conceptual understanding about light. So it's very interesting that Planck almost never accepted the discreteness means particle nature. It was rather it was rather Albert Einstein who used the work of Planck's, and he took these particles of light as particles for the first time, and explained his photoelectric effect. And in here he used he explained the energy emitting in the photoelectric effect as h nu, taking the photon energy and minus work function phi, and this gave the energy of the emitted photons, and which had further having a momentum p, which is h bar k. Now, these two gentlemen made the light in nature as particle made up of particles. And this particle had energy, which is discrete, like n multiplied by h nu. And these particles had momentum, which is h bar k. So this tiny particle is real momentum, which is transferred from light to particles, and then the particles become faster or slower. So this is something which is very interesting understanding which came. Now, this simple understanding of light in terms of particles which have energy and momentum were very useful to define what we know at the macroscopic scale and the microscopic scale. So at macroscopic scale, what we have today is the big nano these satellites, which are basically using the radiation pressure push or radiation pressure from the radiations coming from sun and being propelled in the space. So this is a newer generation of satellites which were first launched in 2010 by Japan, and they are named as kites craft or interplanetary kite craft accelerated by radiation of the sun. Icaros, it's named as. So these are at the macroscopic scale, they are using that radiation pressure push coming from the radiation from sun. At the microscopic level, we see that these radiations can be used to control the motion of the atoms, because if the radiation field photon is absorbed by the atoms, so they get a push in the direction of the photon, so their velocity is increased. But if the same photon is released by the atom, so the electron goes from the excited state to the ground state, emits the photon, and in the opposite direction, the atom is going to get a push due to the reverse action. It's an interesting thing. So this is helping the atoms to slow down and get faster due to the absorption of light and emission of light and so on. And so we can cool down atoms to really low temperatures by using optical fields. We shall go in a detailed discussion maybe tomorrow of this phenomena, and we can cool down the atoms to temperature as low as nanokelvin or even picokelvin today. So this is a very interesting thing. So this temperature scale is not seen or obtained or observed anywhere in the universe. So this particular temperature scale is only developed in our laboratories on Earth. So this is a big claim. Now, so the temperature of the particles is connected to the mean kinetic energy of these particles. And when the kinetic energy slows down, so we say the temperature is going down, and then and the de Broglie wavelength is inversely proportional to the average momentum of these particles. So this average momentum is going down, so then it is going to increase the de Broglie wavelength. So as the de Broglie wavelength is increasing, these objects, these atoms, are becoming more and more quantum mechanical in their dynamics. So this is something very interesting. So this has led to develop Bose-Einstein condensate at temperature as small as 50 nanokelvin. This is an experiment which was done in 1994 and very popular. And now these Bose-Einstein condensates are being used in various different industrial applications even today. So we shall have some words also about these in our later discussion. Now, once we have these cold atoms, which are going to have large de Broglie wavelengths, and so they can appreciate the periodicity of the light as well. So now these cold atoms have very less energy, so that they cannot really move faster. So this way they are able to see the periodicity of the light and appreciate it. So this makes it possible for the atoms to come to the minimas of the potential and sit there. This is condensation. So if we have the condensates in this standing wave field, so these condensates occupy the minima of the potential and stay there. So this makes it possible to develop optical crystals as well. Sometimes it's named as and prototype of a conventional crystal as well. What we have. So if we compare it with this our existing knowledge, so we can write the potential which is provided by the optical field in the form of a periodic potential. And this blue line is showing the wave function of the atoms. Now, these wave functions of the atoms are sitting at the minima of the optical potential. So what we see that the minima of the optical potential takes the maximum population of the atoms. So this can be compared with crystals where we have atoms or ions with valence electrons are sitting at the potential minima, which is around those atoms. So if we compare them, so we see that these optical lattices with atoms inside make a very good prototype of electrons in real crystals. So this makes it possible to say that we are in a position to make ideal crystals using optical fields and ultra-cold atoms. So in here we have a prototype of our crystals available in our conventional use. But the advantage is that in this setup, we can adjust the spacing between two minimas because it is only depending upon the wavelength of the light. So we can make it less or more according to our use. We can make these atoms less or more because they are basically our condensates. So these are the wave functions. So this setup is just like an ideal crystal because it has no impurity. And developing an ideal crystal in our solid state is a very expensive thing. So here we have this for free in a sense. So these are sometimes named as the optical lattices and optical crystals if we go to the three-dimensional. So this kind of setups are also named as a quantum simulation. So we simulate a real setup in another prototype and which has all the main characteristics of the real system. And we can use them at our layer. Okay, now the same setups which we develop here, then take us to develop the qubits, because we can easily control the electron position from ground to the excited state, and that would be providing us these qubits, and we can develop the quantum computer cores using the qubit, single qubit, many qubit systems. So these are various different applications which we can think of once we have ultra-cooled atoms in our discussion and control them. So this makes the layout of our book as well. We have divided our book, which we are talking about, in 3 parts. In part 1, we talk about the basics, fundamental characteristics, and then in part 2, we go to the application of these fundamental laws, fundamental concepts, and apply them in developing various different kind of devices, which are based on the atomic interaction in the periodic optical potentials or exponentially decaying optical potential, where we obtain the mirrors, beam splitters, and reflectors, and so on. And then we talk about the nonlinear Schrödinger equation, which is very popular in the discussion of Bose-Einstein condensation, and so on. In these systems, as we were talking in the beginning, that it is possible to generate some external modulations in a controlled way. The appearance or generation of external modulation in these systems would provide extra parameters and extra mechanisms to control our system. So it gives us more degrees of freedom to control our previous system. So this makes our third part of the discussion, that in the same previously known periodic potential, if we introduce some external forcing, so how the evolution changes, what are the new things, what are the newer control we obtain, and how they help us to generate some better understanding about the atomic dynamics in these optical systems. And then we have some application of the radiation pressure force at the macroscopic scale as well. So you should keep that nano satellite in mind, and there we shall apply. So in our discussion on our technical side, we start with the quantization of the light. So once we say we want to talk about the quantization of light, we want to see in how many ways we can understand electromagnetic field in the quantum mechanical way. And while developing the quantum mechanical nature of light, we go beyond the Maxwell equations, perform the factorization of our wave equations, and obtain the annihilation and creation operator, and write our energy and momentum in this simple form. So this is something which is becoming the second chapter of this book. So in here we talk about various different kind of states of our electromagnetic field, which are quantum mechanical in nature. For example, number states, once the field intensity is very, very small, so that we can even count the number of field photons, we say them as the number states. So we have a good discussion of this in our second chapter. And then we have coherent states, and these coherent states are basically talking about the high intensity fields. The field is intense enough that when we apply annihilation operator, which actually reduces one photon, it does not affect the field itself very much. So after applying the annihilation operator on coherent state, it remains the same. So this is something as we interpret or explain. So the field intensity is high, so that reducing one photon will not make any big change in the state. So that's why we can find it. And then we have Schrödinger-Cat states, where we have superposition of these two coherent states and so on, and then squeeze states. So these are the topics which we discussed as under the discussion of quantum mechanical electromagnetic fields. Our classical field, as we can say in the as a counterpart of this, is just the field which you see around us all the time. It's coming from any classical source. And the quantum mechanical field is a man-made field for particular uses, for for particular requirements. So this again a way of understanding the classical and the quantum mechanical fields. So again, when we want to understand the interaction of electromagnetic fields with matter, we can divide our discussion in two parts. One, where we talk about the discussion of our conventional classical fields with matter, and matter is composed of atoms. And second, we can say that we have specially built electromagnetic fields, as for quantum mechanical fields, and they interact with the material or matter atoms. So once we enter into the discussion of interaction, we have these two classes coming immediately in front of us. So with this, we go to the next part of this, that if we want to understand the atom field interaction, we can have a simple model for our atom, which is a Bohr atomic model basically, and it's telling that electron resides inside an atom on various different levels. And once it jumps from lower level to higher level, it absorbs. And once it jumps from higher level to lower level, it emits. So this is a simple picture we can have at the moment. And this field is a field which is coming and interacting with this atom. This field can be, as we are discussing, it can be classical or it can be quantum mechanical. So if we have this as the classical field, so and the atom is quantum mechanical, so this kind of interaction is named as a semi-classical interaction, because atom is treated as quantum mechanical, but field is treated as a classical. It's coming from any conventional source, which is around us everywhere. It's sun, it's light, and it's any source we have. If you want to write this system in a mathematical way, we develop the corresponding Hamiltonian. So Hamiltonian talks about the atom, and Hamiltonian talks about the interaction of the atom with a field. And this interaction between the atom and the field is written as a dipole interaction, because once the field is being absorbed by the atom, electron jumps from its natural position, goes to the higher level, and develops a dipole. Now that dipole is interacting with this field. So normally we can write the dipole interaction Hamiltonian to describe the atom field interaction. And then we can think of our initial, then we can think about our system state at any time in this simple form, that it is either in the ground state or in the excited state, and then the time may vary, or the probability amplitudes may vary in time as the interaction happens. So we can write this as if we talk about the initial state, so then we have to put t equals 0. And if we want to talk about the evolution in time, so then we have to calculate this psi g and psi e, which are time and position dependent. So if we enter into this discussion, we solve the corresponding Schrödinger equation as per simple approach, and we obtain the unknowns psi g and psi e, which are there. So once we do these calculations, so what we obtain, I'm not entering into the complete solutions I'm writing, but I'm simply describing physically. Once we look at our atom and we, with the help of our mathematical equations, so what we observe that in exact resonance, when the field frequency is the same as the transition frequency, we see the electron in the ground state and the electron probability of electron in the excited state following sinusoidal law. That means if the electron is in the ground state, the probability of the being probability of electron being in the ground state is 1. So probability of electron being in the excited state is 0. So this way, as we proceed in time, it changes periodically following this Rabi oscillation. Now, interesting thing is that Rabi oscillation is the oscillation frequency which controls the dynamics or evolution of electron between ground and the excited state. So this is depending upon the dipole moment, and this is depending upon the electric field amplitude. And at the same time, it's also depending upon the alignment of the dipole with the electric field, because there's a dot product coming in between. So now it's very interesting that if we can control the alignment of our atom with the field, we can adjust also the Rabi frequency. So this kind of discussion or this kind of control is very interesting in case of big molecules or big atoms. So in case of molecules, we can have this alignment in control, and that can help us to define these probability transition between ground and excited state. And then at the same time, the big atoms can also do the same job. So this is something which is coming once we understand the semi-classical discussion of atom-field interaction. Okay, if we want to talk about a semi-classical treatment, but far off resonance, if we are far away from any resonance, so what happens? Now, this is a good question. Previously, we were observing a resonant phenomena. The transition between electron, the transition of electron between ground and excited state following periodic law was basically happening once we were having the exact resonance. But if we are away from the resonance, so what happens? So it's a good question, because this is also a possibility, and very often we can see this. So in that case, we find that the electron, the first thing we can think of, that the population of electron would not go to the excited state, because if it is in the ground state, so the field is not sufficiently enough, the field energy is not sufficient enough to fill the gap between the electron, between the ground state and the excited state. So that implies that the probability of the psi E dot, that the change of probability amplitude of excited state in time will be 0, and the change in the probability amplitude of excited state in with space is also going to 0. So that simply implies electron would not change, the probability amplitude of the electron would not change in space and time once we talk about the excited state scenario. So this secular approximation provides us a very interesting, simple, effective Hamiltonian. Now, this effective Hamiltonian is actually controlling the dynamics of our electron being in the ground state only. It is not possible for the electron to go from the ground state to the excited state because of large tuning. Now that implies the electron would stay in the ground state and will follow a Hamiltonian which is having this shape. So this is a simple understanding, and the kinetic energy associated with the electron will be seen in the first term, and the potential energy seen by the atom due to the optical potential provided will be seen in the next term. Fine. So electron will observe this potential, and it will stay in the ground state. It will not change the state. So this is an interesting thing. So this term, which is the potential energy term, gives us a concept of force as well, which is acting on the atoms now. So this force is having a simple connection between the with the potential as minus del V. So if we apply this simple relationship for the force, so we come up with this with a relation as minus 2 h bar omega r squared by delta, and U is a spatial distribution of the field. It can be periodic. If we have a standing wave field, it can be exponentially decaying if we have an evanescent wave field, or it may take any shape depending upon the field distribution, which is again in our hand. We can develop various different kind of distributions as per demand. We shall talk about this as well in future. So this force is seen by the atoms. It is depending upon position dependent gradient and so on. It's a position dependent gradient force, And the interesting thing is that this delta is a detuning between the field frequency and the transition frequency. So just by controlling this detuning, we can make this force attractive or repulsive. So this is an interesting way that the field can act like an attractor or a repulsor on the atoms just by controlling the detuning. And then U is also available there. It is also, U of R is providing the spatial distribution of the field, and so it can be less or more depending upon the position where the field is interacting with the atom. Now, beyond this, we can enter into the quantum mechanical discussion and the quantum mechanical interaction of atom and the field. A simple addition what we have to introduce while talking about this discussion, that now our field is a quantum mechanical field. This is the only thing, and this the rest is the same. So if we talk about the quantum mechanical interaction between atom and the field, so we have again our discussion divided into two parts, one where we have resonance and once we have far away from resonance. So in case of resonance, we start our discussion with this simple understanding of atom and the field combined Hamiltonian at time t equals 0. So our atom is expressed by psi A, our field is expressed by psi F, and the combined system is separable. So it is it's defined as a product of psi A and psi F. It will be useful to understand our later discussion, keeping this separability in mind. Okay, so if we substitute the understanding of two-level atom, we can write the two-level description in this form. The atom is either in the ground state or in the excited state, it stays there. And the field is written in the quantum mechanical form as a superposition of Fock states, the number states. So we can write any field on the basis of the Fock states in the Hilbert space span by the Fock states. So we can write in this way a general expression for the field. Once we want to see how the interaction will take place and what shall be the changes coming on this atom field interaction, in time we solve the time-dependent Schrödinger equation, apply some mathematical steps as we discussed in the book, and then come up with a final description. So this is psi ENT, which is the combined probability amplitude for electron and the numbers n for the photons. So the atom field combined state for the system, and this is again atom field combined probability amplitude for the system. As one simple check, we can see that if we put t equals 0, so this psi ENT becomes psi EN0, and psi EN0 is nothing but a product of Cn with psi E, and psi Gn plus 1, 0 is nothing but Cn plus 1 and psi G. So this will be a simple understanding which will come in. So confirmation. And here what we see that the Rabi frequency is going to be restructured. It's not just the semi-classical Rabi frequency, which is sitting mu here, but it takes into account the information of number of field photons as n, and the detuning, which is also playing an important role. So something which is useful is that if we want to separate the electron and field at this place, and we want to separate the electron in the ground state information and the field photon here, it is not possible because each term is taking omega n, and omega n is taking care of field photon n and the detuning sitting there. So this actually defines I'm going. Okay, here we are. So this non-separability of this atomic and the field states define non-separability, define entanglement. And in resonance case, when we have delta equals 0, this gives us very simple mathematical control on the qubit dynamics. So qubit dynamics with the help of the field photons can be described very easily in the resonant case scenario. This discussion of resonance is seen at work in various different quantum optical phenomena and also in defining the laser equations as we want to. And if we want to extend our discussion of atom field interaction in quantum mechanical way, and we want to take the discussion to far off resonance. So in case of far off resonance scenario, we obtain our psi of t in this simple way. So in far off resonance, what we should expect? In far off resonance, we should expect that the field frequency is very different from the transition frequency. So what should come to mind that this field frequency is not going to support any transition, because it is not going to take electron from the ground to the excited state or excited to the ground state, because that is very different. Either it is very less. If it is very less, so electron cannot have enough energy to go to the excited state. If it is very large, so again, it is not possible for the electron to go to the excited state. So what should happen that the electron, if it is in the ground state, should stay in the ground state due to the large detuning. And if it is in the excited state, it should stay into the excited state. The probability should not change. Probability of being it in the ground or in excited state should not change once we have far of resonance scenario. Okay, so with this understanding, we look at our description. So we come up with, so this is the final state after the interaction in far off resonance condition, under the far off resonance condition. So here we see if we take n out, we can take, it is common. We can take this n to be common, but then we have E and G state sitting in within the brackets as so that means we have separated the information of n, and the n is a field, and the E and G are the ground and the excited state of the atom. But something is important to note, that these exponentials, they have the phases which are depending upon n, and they are also depending upon mu, which is having the dipole information. So this dipole is coming from the atomic characteristics. So now we cannot separate the atomic characteristics with the field characteristics, because they are appearing in the phase term. So this phase term is appearing with psi En, it is different, and the phase term which is appearing with a psi Cgn or Gn is different. So since they are different, so we cannot separate the atomic information from the field information. And this non-separability is defining an entanglement of the atom and the field in the presence of large detuning as well. So this entanglement we were seeing earlier as well, but that was in case of resonance scenario. So both in resonance scenario and in off resonance scenario, we see this non-separability, and that is the entanglement scenario. So this is one interesting result. And then in again, if we go to develop a corresponding Hamiltonian, okay, now here is our effective Hamiltonian for which is controlling the dynamics of atoms in the far off resonance condition. So if we want to write this complete Hamiltonian structure without going in the derivation, we see that it has again a potential energy term which is depending upon spatial distribution of the field sitting here. It's R dependent scenario, and there are no other terms which are R dependent. So we are not entering into the discussion of the derivation, but once from here, if we want to see what is the amount of the force which is seen by the atom, we follow the same previous prescription that we obtain the force from the potential by taking derivative of the potential itself. So minus del V is going to provide us the force acting on the atoms in the far-off resonance condition. And we come up with an expression which is very much similar to the expression which was obtained earlier. Here we have quantum mechanical information in the form of operators, A dagger A, which is basically the field operator, and this sigma C is the atomic operator. So we know very well A and A dagger separately are the lowering and the increasing operators. So they change the state. But A dagger A is a number operator. It does not change the number. So that means once we have interaction of the atom with a field under far-off resonance scenario, we don't see any change in the field intensity. So it remains the same because A dagger A is only going to give us the number of field photons, for example, there. And then sigma Z is again is not going to change the state. It's neither lowering operator nor increasing operator for the atom. So it's not going to change the state of the system. So it's again interesting thing. So it has, it has the same structure, that it is very much controlled by the detuning. If we make the detuning positive or negative, if we make the detuning, detuning is basically the difference of field frequency, difference between the field frequency and the transition frequency. If you make it a positive, so it will be attractive, it will be repulsive term, and if we make it negative, it will be the attractive term, and so on. So this will be, so the sign of detuning is controlling the sign of force. And then we have this delta U contribution coming, so it is a gradient. So the way we have the larger gradient in the spatial distribution of the field, we have the larger force acting on the particles. So this is a spatial variation of the field is very important. So based on this simple understanding of atom-field interaction, it was possible to define and develop optical tweezers in 1969 by Arthur Ashkin, and he obtained the Nobel Prize in 2018. So this is a very direct application of simple conceptual understanding in the technological development. So this technological development is now used, or by Arthur Ashkin as well. He used his later work on DNA sequencing, bacteria detection, and biological samples. So it was his work. And so I stop here, and tomorrow we shall be talking about the application of okay, in our tomorrow's lecture, we shall talk about development of optical lattices, optical crystal, atomic trampoline, which are seen by the atoms. And then these atoms observe band structures, Bloch oscillation, and so on, and many characteristics. And some basic phenomena jumps in as quantum revivals, quantum carpets, and Talbot effect. So this will be a topic of our tomorrow's discussion. Thank you. Any questions here?
Thank you so much, sir, for your insightful lecture. Okay, it's question answer sessions. Please, first we take question answers from our physical participants. So please share your questions if you have. Yes, I'm here to the.
So does these optical lattices include the minus time of atoms while in the tracking in the standing wave?
Well, a coherence time of atoms would also be connected to the temperature at which they are. So we cool the atoms to increase the coherence time of these atoms. So optical lattice is a configuration in which we place our atoms and confine them periodically. So coherence time would be very much connected to the temperature of the atom directly. So we make them cooler and cooler, they will be there for large and large.
Who are they equivalent to the BECs, like atomic lattices?
Well, atomic lattices, well, BC can be developed without optical lattices as well. But once we have bosons and condensates, we use them in various different configurations, and optical lattice is one of them. So we can develop bosons and condensate without optical lattices as well.
And is there any spin exchange problem while in the optical lattices?
Say it again.
Spin exchange problem while in the optical lattice.
Well, there are various different phenomena.
What happens? So we have spin exchange, which actually lowers the coherence time. So I'm just talking about that. While in that optical lattice, so does there any spin exchange happens there because the atoms are not moving in a like atomic motion or like not a back or what happens?
Well, tomorrow we are going to talk about optical lattices precisely. So there we shall have this discussion.
Okay, thank you. So anybody else have a question? Please. Anybody? Okay, let me ask from our Zoom participants, our virtual participants. Okay, sir. First, sir, I'm not physicist, so if I pronounce the wrong word, so please abandon me for that.
Let me
Oh,
help you there.
okay.
So the first question is why Hamiltonian is not applicable in certain cases like
Quantum
in
dot.
quantum dots.
Yes.
An extension is optical lattices band gap decrease when two different materials are mixed. Why?
Why?
First part is that why Hamiltonian is not applicable. Well, we write quantum dots with the help of potentials, and in many situations we write like one-dimensional box potential for the quantum dots. So that helps us to also write the Hamiltonian for them. It would not be fair to say that Hamiltonian configuration cannot be made, or we cannot write in Hamiltonian for quantum dots. If
Yes.
it gives answer to your question.
Okay, thank you, sir. The next question that is by Hashim Faru. The first question that is asked by the Hamza, and the next question is by Hashim Faru, and he's asking, can we take velocity-dependent potential in effective Hamiltonian?
Well, if we enter into the gauge transformation, we can transfer the time dependence of the potential into the momentum term as well. So if we perform a gauge transformation, carefully transform our Hamiltonian under the gauge transformation, so we shall see that this periodic time dependence appearing in the potential can appear in the momentum term as well, and that is connected to the velocity dependent potential.
Okay, thank you. Okay, thank you so much, sir. Sir, okay, thank you. Today we have that online sessions, questions. Sir, please be seated. Thank you. Okay, tomorrow we also have a second session. Thank you so much, sir. This is a very insightful lecture. Tomorrow we also have the second lecture of this session. So please join us 15 minutes earlier. And for a Zoom people, please bring tomorrow also we have the second session of this lecture. So please join us virtually. Thank you. And please join us for a tea break.